Hello and welcome back to the lab. Today on the bench we have not the frame, but we have two DMMs. This is a DM501 and a DM501A. So this is the 501 is a non-auto ranging. The 501A is an auto ranging meter. Very similar to the 502As that I've used in the lab for a while now. I still need to get one to fill that hole in the power frames to finish up the series of 8. However, let's get some DC going. And we'll just throw some stuff on here. I don't know anything about these meters. I was requested to go give these a once-over, look through them, and do an alignment. The gentleman that owns these meters asked if I'd smash them against my 7510, and that is what we are going to do. But first, let's see if they give us at least some sanity numbers, and don't release the magic smoke. So first off, we'll power them on. And it's okay, we're counting. Everything looks good. The meters are at least not completely out to lunch. So let's just throw 5 volts into it. I'm on the 200 volt range, so we'll go down to the 20 volt range just because we can. This also switched, so that's good. And we'll put 5 volts to it. Okay, so it functions as a meter. It's not completely out to lunch. So that is good. Obviously, we didn't give it a proper warm-up time or anything like that, so overall accuracy is not horrible. The switches on here feel like they need to be serviced a little bit. This rotary switch actually feels okay. Let's check the other one. Let's see. We want to be on 20 volt DC, and we'll give it 5 volts as well. Survey says, yeah, so we have 2 functioning meters. They haven't at least lost their mind. So let's see what we can do about giving these guys an extended lease on life, because they're not dead, so we don't have to resurrect them this time. But just getting them cleaned up and ready for their owner to enjoy. So for part 1 of the video series, we will start with the non-auto ranging meter. This one actually has a pretty prestigious history. This one comes to its owner by the Texas Instrument Company. So I'm sure this meter was well looked after. But let's see what we have on the inside. It's actually, for a meter, it's pretty light. And here we go. So there's not much in here. A couple of no transformers in this one. There is a transformer in the other one. Big tech wafer board switch, cam switch, not a wafer switch. Up here, we have some adjustments over here. Everything looks okay. Actually, I'm looking for some electrolytic capacitors to see if we need to replace any. I know there's 3 of them in a 502 that I like replacing, and I'm not really seeing any. Everything here looks pretty good. And there's a tiny transformer. Input protection fuses, a little bit of a switch we'll have to clean up. Here's our cam switches. These are going to need a cleaning for sure, as all tech equipment tends to do. Nothing looks overstressed. These caps will be fine. The yellow ones, everything looks okay. This capacitor will be fine. Definitely some older style transistors in this one, so a bit more vintage can. Let's see if we have a date code on some of this stuff. 7th week of 78. 6th week of 78. 49th week of 77. So this meter probably comes to us from the late late 70s, so 78, mid 78. So I will reseat these transistors, or the ICs, because I would be willing to bet those are the TI sockets that I have done a video on. But we'll see. Everything did look okay, so doing the alignment on this one's going to be kind of interesting. I'm looking over it as I'm talking here. I got alignment point here, here. There's some caps up here. We have 3 alignment points here. But other than that, everything looks all right. So we'll inspect these capacitors for cracks or anything like that. If we find any, I'll get that under the microscope. If any of them look cracked, they will get replaced. But yeah, everything looks all right. Okay, I've got some switch and contact cleaning done. Gotten everything all situated. I did find a cracked solder joint on one of the input terminals. And I have the DMM hooked up to my curve tracer to do some testing. We're on the 1 kilovolt range, and I'm going to do some things with maximum sketch because everything's open, none of the shields are on, everything's hanging out on the bench, and I'm going to put 1,000 volts to this. Well, 950. So to check it first, we're just going to do some low voltage stuff. Let's go to 100 volts. And I am feeding this in DC. I have the curve tracer in DC mode. Yeah, 100 volts is fine. We'll kick this up to the 1600 volt range. And what we're going to do, there's 260. Man, it doesn't take much for the voltage on this thing to just rocket past. That's 5. 6, 7, 8. There's 9. Let's go up to 9. Let's take it up to 950. All right, 950 volts. So not having any arc over or anything like that. So perfect. Make this safe again before I touch things. And there we go. Power off the curve tracer, and we will power off the DMM. Now, some of the limitations on this DMM. After going through the service manual, because I am going to have to do an alignment on this, and also, when I cracked it open, I distinctly noticed the lack of filtering capacitors or anything else that's in here. Let me zoom in. We have a distinct lack of any kind of bulk filter capacitors and things like that. The DM501 suffers from a condition of being a precise DMM, in which case it can read to 4 digits of resolution, but it is not an accurate DMM. Reason for that is it's not isolated from the main supply at all, and any variation in mains voltage throws the calibration off completely. So whereas even my 6500 or some of my other DMMs, they have a whole lot of filtering and isolation in the power supply to decouple them from the mains and the fluctuations on the mains. This does not. That was something they fixed in the DM501A, the 502A, and previous meters. And subsequent meters. So that's a drawback of this particular meter. However, if we get a DM501A version 2, and we take a look at that one, here's the back of this meter. Here's the back of this meter. You can see immediately regulation decoupling transformer, regulation elements, and then there's capacitors in there that we're going to change out in this meter. So we have a little bit of difference between precision and accuracy. Still a good meter. I mean, I wouldn't mind having one in the lab, but I kind of settled on the A variant. We'll get this all put back together, and then we'll run it through an alignment as best it can be aligned. Okay, before we get into a alignment and calibration of this meter, I don't know if the camera's picking it up very well. I'm going to zoom way in on these input protection fuses, but these fuses have a little bit of the green death on them. So I'm going to get these fuses cleaned up, get that connection better. This is the, actually let me just pull this fuse off so the camera can see it better. This is the cracked input joint that I was talking about earlier in the video. So we put a little bit of solder on that, clean that up. I'm going to get these fuses cleaned up, and then we'll let it warm up for an alignment. I've had the AC and DC standard on for quite some time. The 7510's been warming up since this morning, so it's been on for a few hours. We'll get this up and running. Okay, we have a DMM and an alignment document. So, where is it? Here it is. Here's all the adjustment points and measurement points that we're going to need to take a look at on this particular unit. So, first off, we need to check the 5 volt, the main reference 5 volt supply in the unit, which is pin 24 of U330. So to make this easy, we'll just spin the mat. U330 is this guy right here. Pin 24 is all the way on the bottom next to that resistor that's pulled out and flying off to that other IC. So let's get some good meter leads and probes. Okay, there are the leads hooked up. And we are within spec barely. It's looking for 5 volts plus minus 0.1. We're at 0.11. Here is the meter reading there. So what I'm going to do is I'm going to tweak R420 for the 5 volts adjust. See if we can't tighten that up just a little bit. This is a very old style resistor. So doing this adjustment is going to be kind of fun. And by fun, I mean not. All right, so that's going down, so it's counterclockwise for up. All right, we'll run with that. I like that. Okay, so here is our negative 12 volt reference. VR410, and we look at the 12 volts here, and I have 12.3, so that's good. Now we're going to look at the negative 12 volts here, and I have negative 12.3, so that's good. So our 12 volt supplies are perfect. The probe, I moved the ground to pick up a really good chassis ground for testing. I moved the negative lead of the DMM right into the chassis. So this is a perfect place for doing these for checking chassis ground. However, I need to go. However, we now need to be on these pins because I have to check the floating supplies for the analog board. I'll probably do that with probes because getting some stuff in there is kind of tight. Okay, so on the floating supplies, we're at the bottom of the analog board, and our tolerance here is 0.6 volts, so 600 millivolts, which is fine. We have ground here, negative floating supply, and I'm just within spec, so that is fine. We'll check the positive. Positive is 11.6, so 6.2, so that is also within spec. And we are good there. So floating supplies check out, so now we get into some of the adjustments. One more floating supply. We're now on the negative, or we are on the 5 volt supply, which measures at 5.18, so that is perfectly fine there. Okay, spinning back to the front. we have a shorting bar, and we need to be on the 2-volt range. We would be adjusting the integrator 0, which is R155, which is actually up here. And we need to adjust for a display of all zeros, so we are solid there. No problem. All right, now I need the 7510 because it wants to do the adjustment at 1.8 volts and as accurate as possible. Well, I can do 7.5 digits here in the lab, and so we will, because we can. And because we are working with low-ish voltages, we can get away with sending it up through some high-quality BNC cable, which is also fine. All right, the way we'll start this is the DC calibrator set exactly to 1.8 volts. Where do we settle off? Well, I can't complain about that. Yeah, no complaints there. So we got a very solid 1.8 volts. And we'll go ahead and hook up the DC calibrator to the front end. And we need some adjustments. No problem. So these 3 adjustments are coming out the top of the unit, right up here. The DC plus cal is 182, so it's the middle control. And we need to adjust that for 1.8. Make sure I'm on the middle one, not that I tweak the wrong one, because that's never fun. We're going the wrong way. Now it's bouncing, but I know I have stability past the 1.8, so I want to give it just a little bit more. Come on, get back in there. Come on, get back in there. But there's 801, so I need to come back just a touch. And we'll center it right there, and we will be done. And now we flip it over to reverse the polarity. And do the same thing with 202, which is the control closest to the front. Right here. And this is off by quite a bit, actually. There we go. So we'll just do some spot checks now and see if it agrees. We'll flip this over and we'll pop this to 20 volts and we'll go to 18 volts. That's reading a little high on the 18 volt on 18. But let's check 200. With 180 volts. Yeah, that's reading okay. Now, I am not going to mess with this when it's at 118 volts. I'm back down to 1.8. I do not have, so when you, number 7 is adjusting the temperature offset. I can't actually do that because this unit was not sent with a temperature probe. and the temperature probes themselves have to be calibrated to the unit. So once you have a probe and you adjust the probe to the device, that's where it needs to stay. So those are a pair. So even if I did adjust it with my probe, it wouldn't do any good here. So we don't need to do 7, 8, 9, but we do need to do 10, which is do some ohms checks. So let me get some probes and a decent resistor. Okay, so I don't have a 200 k ohm resistor, but I did have some 100 k ohm 1% resistors. Or actually, sorry, 0.25% resistors. So these are some very high quality 100K resistors. We're on the 200 k ohm. And I have a little bit of discrepancy in my meters. So my DMM6500 said these were 100.06. This is reading a little high. Doesn't surprise me since we adjusted the voltage. However, because I need an extra digit of accuracy, I am going to hit these with the 7510, get a good reading, and we'll adjust to that. Yeah, it was the reference in the 6500. It was bouncing around a little bit. So 100.7.07 is what we're looking for. Now, for the best accuracy, I'm going to use the same leads and everything that I used with the 7510. So the resistance is now known for this combination. If I had changed leads, it could have skewed it a little bit and thrown the alignment off. So we're just doing the best we can. And then ohms cal is R35, which is down here towards the bottom. We need to back this off for 0.7. Wow, that's really touchy. I barely moved that. But I'm going to be happy with that right there. And this is so sensitive, just like moving my hand next to it can cause this thing to move around, just touching the wires. So now we're on to DC current. Okay, so we have the DC current zeroed. It's plus minus 1 count, so we're 1 count high. Now we need accurate current rating, or current supplied, to the meter to check its ranges. And it helps if I'm on the right function, because I am on AC milliamps, not DC milliamps, so that's going to be a problem. So, oh, that's much better. Bring this down to 0. Okay. So now we are on 2,000 milliamps, so that's 2 amps. So I am going to ask my 2281S. Okay, here is essentially 1.80004 amps as said by my meter. The burden voltage on this meter is about 600 millivolts for the current range. So what we're going to do is we're going to turn that off. And it's now 200. So we're going to drop this by a factor of so this is going to go to 0. This is going to go to 1. And 180 milliamps. That agrees actually very well with the power supply. The power supply says 189.84. We're at 189.69, so that is looking good. Now we're at 20 milliamps. So I'm going to ask the power supply for 18 milliamps. And 18.945. Yeah, They are matching very well. And let's go down one more. This is 2 milliamps. Let's see if this power supply can do 2 milliamps. If it can do it, great. It can. If not, I'll have to use the SMU. So we are asking this power supply to output a regulated 1.8 milliamps. And it looks like we can do it. So power supply saying 5.2, 5.4. Yeah, so perfect. Score 1 for the 2281. Okay, so the clock was wandering around on my AC calibrator for a little bit, but there's a phase lock on the AC calibrator, which I have not been able to use yet. However, I did just figure out a way to use it, which is very cool. These guys, which I reviewed in a looked at in a previous video, can actually give me sine waves at a high enough frequency. I was frequency limited on my other function generators, but I can use the 10 megahertz in to stabilize this clock and use the frequency out to stabilize the calibrator clock. Because the calibrator clock does not actually take a reference in, it takes a phase lock. So I have to feed it a signal that is close enough in frequency to the set frequency on the front of the calibrator to get it to mesh right. The other thing that's really cool about the AC calibrator that I didn't know until I looked at the BNCs close enough is it has a counter output on it. So I've run a cable from the counter output up to my 5313A, and I've run a cable from my function generator down to the phase lock in. Turning phase lock on yields these kind of results when it comes to frequency. So I am at 1 kilohertz, and that is much more stable than the native clock in the Fluke 5200A. So very cool. This might become so important enough where I might permanently wire some BNC jacks to the bench so I can phase lock with this regularly. But yeah, I'm pretty stoked about that. Okay, so there's our 1.80006. We're going to hook that up to the DMM and get some adjustments done. I'm going to be adjusting AC Cal R70 for this right here. And we're looking for 1.8. Actually, we can give it 006. I have some dirty pins. Let me put a little bit of contact cleaner on there, move some pins around. That's what was causing the display to go kind of stupid. So need to clean this up, and we'll be back. Okay, after cleaning up the contacts to make the AC behave, we're at 1.80010, 1.80010. And there we go. If I tweak that much more, it's going to settle off around 1.80 7 to 13. If I tweak that anymore, it's going to dive to 1.7997. So this is about as close as we can get to the true number. There you go, 1.80010. So that hit just right. Let me get this moved back over to the Fluke, or the Keithley. And we need to bump to 20 volts AC, 18 volts RMS of 8 kilohertz. So we need to bump up the frequency counter to, or the function generator to 8 kilohertz. That's going to cause the phase lock to go kind of bonkers because I need to raise this to 8 kilohertz as well. And then we also need to go to 18 volts. So set this to operate, external sense, phase lock on, local control. And we're going to trigger the 7510. Let it figure things out. We are at a nice and stable 8 kilohertz, as confirmed on the frequency counter. And we're at 18003. Bump this up. We do need to adjust a little bit. So we need to adjust C42 for the 20 volt side. Oh, I gotta get in here by these wires. This will be better if I lay it on its side. So we'll do gently. Oh man, that's gonna break my tuning tool. That one is stiff. Do we have for non-low capacitance screwdrivers? There we go. Now we're moving. Switch back to the tuning tool. Okay. Wow, this control is really, really stiff. See what I mean about it just kind of falling around? These are kind of touchy. That's going to be as good as I'm going to be able to get it. Try this one a little bit. I need to kind of see 8004. Oh, it's 8003, not 803. Oh, man. Also helps if I tune to the right. Helps if I tune to the right value, you know? Funny thing is, it's kind of almost... This is just the flex in the tool is jumping it a bunch of counts. Just playing with a little bit of capacitance on this one. Not sure which tool's working the best. Let me get in front of this, and I'll bring you guys back when I get adjusted. That is about as good as I'm going to be able to get that capacitor, but I'm not unhappy with that. That took a while. Okay, I had to turn the 5205 on. That's what the additional fan noise is here in the lab. I don't know if the mic's picking this up at all. The bench just got really spicy. I talk about safety in a few videos and a couple of other things. Note the KV. This is 108 volts AC at 8 kilohertz, so it's a lot faster than what's coming out of the wall. The amp that I have this plugged into is capable of outputting 1500 volts AC. This is starting nothing to sneeze at. Here's the two units operating. You can see the giant lightning bolt. You can see the operate, and you can see all the other fun stuff that goes with it. I'm not even going to move this voltage from the DM501 to the other meter with this on. So to move the voltages, I have to come down here, put the unit in standby, which turns off the operation. I know it's at 180 volts, so then I can move the BNC down to the meter. I'm not pushing this cable very much because this is a very high quality BNC cable, and this is only 180 volts. Much more than that, and I'd be looking at some specialty cables, especially if I have to use this big guy at his full rated voltage. That's actually a fixed high bandwidth amplifier, so you don't even need the 5200 to use it. There's a that red cap, the yellow cap over here. That's a input where you can just put a waveform in the front of it, and you get 100x out the plug. It's a fixed 100x amplifier. So I've got everything moved. We'll kick this back on. Helps if I put it in the right range. Kick this back on. And we are at 180 volts. So I'm going to tweak this a little bit. Now I have to be extremely careful now because there's 180 volts here. There's 180 volts all over in here. This has just gotten really spicy. So safety is of the utmost. Oh, God, I got to go up to 450 volts RMS for the 500 volt. Okay, so we're going to do the 200 volt, and then we'll do the 500 volt. Okay, there we go on the 180 volt range. Now I need to set up the bench again for the 450 volt range. This is getting a little ridiculous. And as we fire up the lab and raise the lethality of things, 450 volts. Now I do know that this is 450.00. So we need to adjust the 500 volt compensation, which is here. And there we go, 450 volts even. Now, I'm going to get all this stuff turned off because I don't mind working on voltages like this, but I don't like them laying around. Okay, that concludes the alignment and adjustment and repair of this DM501. Of the TM500 gear, I actually like these solid side panels a little bit nicer than the non-solid ones, the perforated ones. The perforated ones are better for airflow. However, for things of this sensitivity, like a meter or something, these solid ones are better for noise rejection. But who knows what these things actually shipped with. I'm sure these are the original side panels for this one at this point, but these things change hands so many times over the years. Thanks for stopping by, taking a look at the repair-ish. This one didn't have many troubles, other than unlike some of the units we've gotten. But the alignment for this DM501, and I hope it gives its owner some nice long years of use. That's it for now, and I will see everybody in the next video. More is always on the way.